The next talk is by Abel Thayil. He's a graduate student working with Marcel Foloche at École Polytechnique, and he's going to talk about hopping transport in disordered systems. Abel, would you unmute and share your screen?
All right, do you see my screen?
We can, and we can hear you.
Okay, so hello everyone, my name's Abel, and I'm a PhD student under Marcel and Jacques. I'm going to be talking about hopping transport in disordered systems. So I'm going to start by telling you why we're interested in hopping transport and what it is exactly, and how the localization landscape can apply. So when we talk about transport in semiconductors, we're usually referring to what is called band transport. And this occurs when you have large carrier concentrations and at high enough temperatures. So the electronic states that are contributing to the transport are delocalized. And so in the diffusion equations, the parameters that go in, like namely the mobilities, they are the bulk mobilities. So you have mu and the mobilities of holes and electrons that are bulk mobilities. So localization plays a role, and this was accounted for by previous work of this collaboration, namely via the Poisson landscape loop. But we're interested in a different regime of transport, which is called hopping transport, that occurs in for lower carrier concentrations and for lower temperatures. And as you can see, this happens when the electronic states are localized. And so for them to contribute to the transport, electrons have to hop from one localized state to another. And so both these transport mechanisms have different signatures. And for example, the way the mobility would change with temperature varies significantly. And so this can be detected. All right, so hopping transport is essentially when electrons hop between localized states. And to give a more concrete example of this, say I have a 2D disordered potential in a 2D domain over 30 nanometers by 30 nanometers, where I've sampled V uniformly between 0 to 1 electron volts. So you get localized eigenstates. I've plotted the first 5 here. And to better illustrate my point, I take a sort of 2D projection of this. So the question is, say an electron finds itself in one of the localized states, psi 2, say this green localized state. How does it hop from one state to another? And how do you study the dynamics of this? So the first thing we do is we introduce these transition rates. Wij is the transition rate between two states, psi I and psi j. And this is determined by the degree of overlap between these states. And so certain states contribute more to this transition, others don't. And another thing that we use is the average occupational probability, Fi. So how likely are you to find an electron in one of these states? So to study the dynamics of this average occupation probability, you introduce these hopping master equations. And all this is really it's a conservation of probability. So the way this occupation probability changes with time is a sum of all the transition rates outside of it minus all the sum of all the transition rates inwards. The sum is over J over here. There's an additional caveat, which is that a hop can only happen to a state that's unoccupied. So there's this 1 minus Fj term. So if that state is already occupied, it's going to contribute very less to this master equation. So the problem reduces to finding the steady state occupation probability. So when the left-hand side of this equation becomes 0. Another way to think about this is to think of an effective resistor model. So where you have each of these localized eigenstates form the node, and the resistance is connecting them, and some resistances are greater than others, and the electrons would take the path of least resistance to get around. So this effective resistor network allows you to calculate, say, a current in response to an applied field. And these are quantities that we're interested in. All right. So one way of creating these networks that is quite common in literature is called the Miller-Abrahams model. And the Miller-Abrahams model gives you these transition rates between I and J, between states I and J. So it gives you these Wij's that connect these different localized states. And I'm going to focus on two of the important ingredients here. The first in blue is this exponent minus Rij over A term, which essentially Rij is the distance between the localized states. And what this says is that the transition rate decays exponentially as you go, as the distance between the localized states increases. And this reflects the fact that your localized states also decay exponentially. So it's understandable that that would happen. And this is modulated by this average localization length of the system. Often this has to be guessed, and we don't have a good estimate of this. Then this red term here, which comes from the detail balance conditions, but you can think of it as a distance in energy space. And so what this means is, so you might have two states that are quite close. If they differ in energy, that still might be an improbable hop to happen. So it would contribute less. All right, so the landscape, so where does the landscape come into this? The landscape function gives you an effective potential, and we know the minimum of these potential correspond to the localized eigenfunctions, and they also give an estimate of those eigenvalues. So they help you construct the nodes of that network I just described before without having to solve the eigenvalue problem. And in addition, because they help you define, because you have an accurate bound on the decay of these functions by the Agman distance, you have a good estimate of how these functions decay, and this good estimate gives you a way of explicitly calculating the overlaps between neighboring states. And these overlaps allow you to calculate the transition rates. So for example, here I have an electron-phonon interaction that couples the two localized eigenstates. Phonon is essentially a vibration of the crystal. So again, just to summarize this, we have these two main ingredients here. The landscape function allows you to explicitly calculate the overlaps and replace this average sort of localization length. And it also gives you the energies via the minimum of the potential. Over here, you would have to guess a density of states for your localized states, and the transport is quite sensitive to this. So the localization landscapes allows you to calculate these transition rates explicitly for one realization of a disordered potential. So to conclude, our global goal here is to sort of is to have both regimes of transport, when you have the semi-classical drift diffusion equations, and when you have hopping transport in the relevant regime of low carrier concentration, low temperatures. And so I'm currently comparing mobility curves between mobility curves that I get from the Miller-Abrahams model, from the true Schrodinger solution, and those predicted by localization landscape theory. I don't have those plots yet, but I'm confident they'll be coming soon. And right now I'm working with 2D systems, and so the goal is to extend this to 3D systems and use parameters that are relevant to nitrides as well. So thank you for listening.
Thank you very much. Nice talk, Abel. And the floor is open for questions.
This is Jim. I have a question. Very nice, Abel. Maybe it's a series of related questions, but first, how do you, for the landscape, how do you apply bias in these calculations? How are you going to apply bias to the system?
Okay, so you mean like a potential difference?
Yeah, you need, I mean, yeah, you need to bias the system, right?
Yeah.
And
So
then everything changes a little bit or
right.
a lot.
So we'll have to work at low biases because we assume that the localized eigenstates don't change much.
Okay.
But here the bias would appear in this EJ minus EI term. So this difference in energy would now be EJ minus EI minus the field times the spatial distance. So so you would have this field assisted sort of. So now detail balance would be broken, and so you'd have more transitions in one direction or over the other.
Okay, but will you, with landscape now, when you bias, can you just tilt the landscape and see the change in the overlap of, say, psi j, psi I?
So I haven't done that yet.
Okay, but if I may intervene, the usual definition of conductivity is you take it first for oscillating field, and you take the continuous conductivity is when you omega, the pulsation, goes to 0, and when the field amplitude goes to 0. So it's some kind of it's the continuous conductivity, the DC conductivity, that's actually defined like this. So now after, if you are looking for nonlinear effects, you have to compute the landscape with the electrostatic field, as Abel mentioned. I think that in the first, as a first step, the DC conductivity at very low fields would be a very interesting to measure already.
So then the other question for Abel, are you directly, I mean, when you have the hopping, do you really go directly into this, say you go from state J to I or I to J, are you really going directly to that state, or you go to higher states and then relax down? So still you have a localization potential, but you have many states, you know, you have a ground state, but you have many states going up in a localization regime.
So this is,
yeah.
Right. So for the time being, I haven't done relaxation. I'm doing direct transitions between I and J.
Okay. So when you look at, what do you call them, Marcel? You're looking at the tribe of fundamentals, but we haven't looked at the tribe of loose hoodlums, you know, the excited
Yes.
that are out on the loose.
But then also you have to understand that going through a third state or intermediate states which are higher in energy, first it depends on the temperature. It will be costly. You know, if you are at the current temperature, if your excited states are above 25 millielectron volts, then it's much higher. It's much higher in costs. So it's all the balance between how thick is the barrier, how high is the barrier, whether it's more profitable to go through a higher energy state or go directly tunneling from one state to another.
But when you look at the Miller-Abrams formulation, you don't see
Yes.
the barrier. You don't see the barrier. You don't see any barrier.
It's in the Wij. The ARJ that is there, it's not a distance in space. It's a distance. It's the sort of the Egmont distance. It's the distance.
Okay. Oh, I see. This is a.
This is where you have, you know, really how they are coupled. It's a coupling coefficient.
Okay, so it's not a physical distance.
Yeah.
Okay, or it's partly a physical distance. It's a sort of this work, you know, force times distance,
Exactly.
right? Yeah.
It accounts for the thickness of the barrier.
Okay.
Any other questions for?
yes, this is Richard. It's a very interesting talk. One of the old problems with looking at hopping transport is that almost always the characteristic localization length was quite short, and pretty much the shortest distance it could be. And presumably one of the things you can do here is really explore how that could be a larger length. Do you have a view of what sorts of lengths you will be getting? I presume that would be in terms of numbers of lattice spacings.
So right now, these characteristic localization lengths, I mean, depend on how, I haven't experimented with a lot of potentials, but it depends on how correlated those potentials are. And that's really what determines for my, I mean, few experiments that I've done. I haven't, I don't have a good answer to that question yet, but that's something I'm definitely looking at, how the potentials affect this characteristic localization length.
Thank you. Yep.
Any further questions?
I have just a purely technical question, and it happens to be on the very slide that we're on right now. So the interaction between the two states is mediated by this operator, which is the electron phonon operator. So as a mathematician, I don't know what that one is. I'm assuming you have some surrogate for calculating it, even in practice but I don't know. What is it exactly?
So it looks like an EIQ dot R for, like, say, phonons.
And so what is it? It amount to taking the integral of the absolute value of those two states as opposed to their inner product, which of course would just be 0.
I don't see why that would be.
It's more the Fourier transform, the special Fourier transform of the product.
So
of course, if Q equals 0, then you get the real inner product, so it's 0. So you need a phonon with a non-zero wave vector, but sort of it looks like the Fourier transform of the product.
I see. So you have an extra pure exponential factor,
exactly.
and which is related to somehow the frequency or the wave number of the.
It's a wave vector that is you have a momentum conservation.
Yeah, I see. Okay. All right. I got an idea of what it is. Thanks.
Okay, any last questions? Okay, thank you very much.